Today we're going to talk about 1.3, evaluating limits analytically. The first thing I'm starting off with is the properties. I do want you to get these in your notes. The one thing I'll say about them is they're really intuitive. Sort of the way you think things should work with limits is the way they do work. This is actually quite a luxury because down the line we'll be dealing with concepts that aren't as friendly in that regard. Okay, so something to keep in mind. But basically, for the sake of having your notes have everything you need here, I suggest writing these down. Basically, we're starting off by defining these two different limits that allows us to sort of see what's happening with these properties. So the first one, the limit as x approaches c of f of x is equal to L. And then the limit as x approaches c of g of x is equal to k. Okay, this first one is if I put a constant out in front, b, lowercase b typically means a constant. In fact, just something for future reference, letters at the front of the alphabet like A, B, C, D, etc. Tend to be constants. So the limit as x approaches c with that constant is just the limit L from that times b. So once again, pretty intuitive. Same thing here, the limit as x approaches c of the sum or difference of those two functions f and g ends up being the sum or difference of those limits. Like I said, it kind of works logically. Same is true for multiplication. The limits just get multiplied. All right. Same is true for division. Keep in mind that k should not be 0. If k is 0, then we've got to go to different means to figure that out. That will happen sometimes. We'll sometimes have zeros in denominators, but that's just something we have to deal with. And then we get over here dealing with things that have like composite functions. Here, if we take f of x and we raise it to a root, it ends up being the limit of L raised to that root. That would work for, roots or power. It could be either one. Of course, powers and roots. Roots are just fractional powers, so it ends up being the same. If we do composite functions, we can just move that limit inside. So notice what I did here, I moved that limit inside so we can focus on the limit as x approaches c of g, which we know is k, so that ends up being f of k, and the same is true in reverse. So for the most part, as we work through these, you're going to see that this just means that limits play nice. They actually are quite nice in this regard. Okay. All right, so let's move on to doing some actual algebra with these things. All right, let's do some examples. Really, since we're doing things analytically, that typically means algebraic. Last video, we talked about things graphically and numerically. In this class, that's pretty typical. You want to understand things both graphically, numerically. So numerically means tables, and then algebraically, analytically, and then ultimately the overall concept. So basically 4 different ways we want to approach everything. Now let's be clear, any of these you can just simply graph and look at like we looked at with the last section, 1.2. But sometimes we don't have access to the graph. We want to be able to think our way through this. Okay, so I start off with these for a particular reason. For the most part, most of these are what we call continuous. For instance, if I graph this is just a parabola. It's got no breaks, it's got no asymptotes, it has nothing like that. So as long as the function's continuous, then the limit is actually just the point evaluated. So we can just plug 1 right into this, and we're going to get 0. Now let me use a different color here. Okay, so we just plug in the value. Same is true here. If you think about cosine graph, it just goes like that, it's continuous throughout. If I plug pi into this, I get -1. That's going to be the limit. Same is true here. I can just plug 1 in. So I get 2, and that's over 3, so that's 2/3. Okay. And so typically, if I can just plug in the value, that tends to mean that it is continuous there, and that is actually the value. I want to caution you, however, that remember from last video, as I talked about, just because the function has a particular value does not mean that's the limit. The limit is what it's approaching on both sides. Now, when it's continuous, it actually gets to that point. Now, this one is one that people will make the mistake of thinking that's 0. I can plug 0 into that. That's equal 0. But that's not the limit. And the reason why is if I look at the graph of y equals square root of x, right, it looks like this. From the right, it certainly is approaching 0. But from the left, it does not exist. So this limit does not exist. So once again, let me recap that typically if you can plug in the value, that means it's continuous and that's going to be the limit. There are the odd cases like we see here where we can plug in the value. F of 0 does exist, but it's not equal to the limit. Okay? All right. Now let's transition to more of a typical type of scenario. We do want to be conscious of dealing with limits with continuous functions, and there's some reasons why we want to understand that for sections that are upcoming. But the real power of limits is it allows us to evaluate something that isn't something we could evaluate under normal means. Okay? So for instance, if I look at this particular function here, if I plug in 4, I get 0 in the denominator. Okay? But what I can do is realize that I can simplify this, right? I can factor this. So the top is going to factor as a difference of 2 squares. Okay? And actually, the 0 in the denominator can cancel. Now let's be clear about this. This function right here is not equal to x plus 4, but the limit is. And that's the important thing. So the limit here is equal to 8. These functions agree for all but one point. So if we were to graph this function right here, and you can try this on your graphing calculator. Once again, your graphing calculator is going to have some glitches with things that are called holes, right? So it doesn't do holes very well, and that's exactly what's going on here. So if I graph this thing, okay, I get something that looks like this. So this is what that graph looks like. So the limit's equal to 8. So it is identical to the function x plus 4 all but one point. So I could actually redefine this thing, and at some point you'll see this as a piecewise function. I could call this x plus 4 for all values, x not equal to 4. And x equals 4 simply doesn't exist. Okay? But the limit is not impacted by that. Once again, remember when we talk about limits, it's what it's approaching on both sides. So it's approaching 8 on both sides. It doesn't matter that we get the 0 in the denominator. Okay? So let's move on to some other examples. Okay, we have 2 more examples here. So once again, when we're doing limits, and we don't have use of a calculator or a graph or something like that, and you want to do these analytically, basically just some steps. First of all, see if you can plug in the value. Typically, if we can plug in the value, that means the limit exists, and it's equal to that value. Now, I did give you that exception before, the square root of x, but generally, if you can plug it in, that's going to be the limit. Here, of course, we get a 0 in the denominator. Actually, both of these, we get a 0 in the denominator. So then the question is there an algebraic way to remove that 0 in the denominator? Is there a way to rewrite this thing so it doesn't have that problem? As we saw in the last examples, 5, we could factor out the top. That's going to be one of the more common ways you're going to remove that 0 in the denominator, which is what we're going to do here. So we can rewrite this thing as right? So I can factor the numerator as a quantity x plus 4 times the numerator x minus 2. So these are going to cancel. Now, once again, let's be clear. This function is not equal to x plus 4. So this function here is not equal to x plus 4. It's exactly the same for every single point except for one point, and that is at 2. It has a hole there. But once again, it doesn't matter what actually happens at the point with limits. It's what it's approaching on both sides. So this is equal to 6, and that's what our limit is. Okay? If you want to confirm this, you can go ahead and look at the graph, look at the table, see if that matches up and gives you 6, which you should. Okay. Number 7, this one's a little bit more complicated. So once again, we have that 0 in the denominator. We can't do something as simple as we could in example 5 or 6 where we just factor it. However, this is a trick that works and something you might remember. When we have, you guys would have done this like in Algebra 2 or Geometry when you had radicals in the denominator. You do what's called rationalizing the denominator. When you had something that was an expression like this, you multiply by something that was called the conjugate. Now, we're not trying to get a radical out of the denominator. We're just trying to get something. By the way, I wouldn't expect you to see this or be able to do this without seeing it the first time. But what I'm going to do is, just like I was trying to get the radical out of the denominator, I'm going to multiply top and bottom by the conjugate. The conjugate, same term, same term, same term, same term. Instead of minus, it's going to be plus here. Okay, we're going to multiply top and bottom by that. Now what ends up happening here, when I multiply the top, I'm going to multiply this times this. And if I multiply radical guts times radical guts, I'm just left with the guts. So that gives me x plus 5, or excuse me, x plus 25. Okay, now when I multiply the inner thing, I get negative 5, the quantity, the radical. And then on the outer, I get plus 5. So those will cancel. And that's always going to happen. I get negative 5, same thing, plus 5, same thing. And then finally, these two last terms, and however you multiply them, if you want to use the box method to see that, that's fine. Negative 5 plus 5, multiply those together, we get negative 25. Now, in the denominator, I'm just going to leave this as is, because we actually are going to be in good shape now. Okay, so don't go factoring this. What we're ultimately trying to do is cancel out this x. Now, if we've done this correctly, what we're left with is an x in the numerator and an x in the denominator. So I can remove that 0. That problem goes away. Now I have a new function that agrees with this original function in all but one point, the point that was giving me a problem. So there's nothing keeping me from plugging in at 0 now. Piece of cake, plug 0 in, I get 0 plus 25, that's 25, square root of 25 is 5, so I get 1/10, and that is our limit. So let me, once again, review. When we're doing limits sort of blind without a graph or without a table, try plugging it in. If you can plug it in, that typically is a limit, typically. If you can't, if there's a 0 in the denominator, see if there's a way to remove it. Most of them you're just going to be able to factor. In a case like this, I key in on the multiply top and bottom by the conjugate. That does end up working, and we're able to remove the problem. Okay, let's do one last example, and then we'll move on to what is called the squeeze theorem. Okay, so once again, we have a limit. We don't have a graph. Notice, try to plug in the value first, see if it's continuous. This one is not. We get a 0 in the denominator. So then the question becomes, can I find a way to algebraically remove that problem? We can't factor here. We can't do the trick with multiplying by the conjugate. But what I do realize is we have what is called a complex fraction here. So that is fractions within fractions. All right. Now, the easiest way to do this, I've seen people in the past where they combine the top, get a common denominator, and then deal with it from there. What's actually easier is multiply top and bottom by that common denominator to knock it out in one line. Okay, so notice I can multiply top and bottom by the quantity 4 times the quantity x plus 4. And now, of course, it's a fraction, so what I multiply to the top, I multiply by the bottom. Now, what's going to happen here is I'm going to distribute this through the top. So when I multiply this by this, the quantities x plus 4 cancel, and I'm left with just 4. Okay? So once again, right, the x plus 4s cancel, and I'm just left with the 4. Minus, now the 4s cancel, and I'm left with the quantity x plus 4. In the denominator, similar to when we did the conjugate, we don't want to go factoring, or excuse me, distributing this thing. We want to leave it as is. So 4x, x plus 4, because ultimately, keep focused on the x, we want that ultimately to cancel. Now we're in business. So if I distribute the negative, I get 4 minus x minus 4 over 4x, x plus 4. The 4's cancel. I'm left with the limit as x goes to 0, negative x over 4x, x plus 4. Okay, and the x's now cancel. Now we've got it. Now remember, if x cancels here, I'm left with 1. So now I'm left with the limit as x goes to 0 of negative 1 in the numerator, 4, and the quantity x plus 4. Now there's nothing holding back plugging in the 0. Plug the 0 in, we get negative 1/16. Okay, so moral of the story is try to plug in the value. If you can't, if you're getting something like a 0 in the denominator, see if there's a way to algebraically remove that problem. Let's talk about squeeze theorem. Okay, so squeeze theorem up here, want to get this in your notes. If h of x is less than or equal to f of x, which is less than or equal to g of x for all x on an open interval containing c, except possibly c itself. So c, you know, if this is true for all values except c, the squeeze theorem will still hold. And if the limit as x approaches c of h of x and the limit as x approaches c of g of x agree, they equal L, then basically we know then that the limit as x approaches c of f of x must also have to be L. So the whole idea here is, let's say we're ultimately interested in the limit as x approaches c of f of x, okay? I don't necessarily know what that is, okay? So I have this function f, I don't necessarily have access to it. But what I can do is, I have these two other functions, one that's always less than and one that's always greater than, and those two functions do agree on this value L. Okay, I leave this open because we don't know what's happening on that. It doesn't matter what happens at C, as always with limits. What actually happens at the point is inconsequential. So this would be our G, all right? And this would be our H. Then what happens, because they always have to have this relationship, the F gets squeezed through that limit, forcing F to have the limit of L through that point. And that's squeeze theorem, okay? So when do we use this? I'll show you here in a moment, but basically it's kind of a contrived situation. We're looking to find what the limit of f is as x approaches c. We don't know what it is, but what we do is we squeeze it through two known functions, one being above and one being below, thus squeezing the limit to have the same limit as those two functions. All right, let's take a look at an example of that. Okay, so now we're going to use the squeeze theorem to actually show the limit as x approaches 0 of x, or actually find the limit as x approaches 0 of this quantity here. This is actually number 99 in the book. I paraphrased the squeeze theorem here. So once again, h is less than f, which is less than g. We're ultimately looking for the limit of f. We know that these two limits agree, they're equal to L. And finally, we have this value that we're trying to find what f is, thus forcing it to be that value L. Okay, so now I want to know what this is. Now the book actually tells you this, you don't have to worry about this, but what I know is the negative absolute value of x is less than x sine of 1 over x, which is less than the absolute value of x. Okay, now really we just need an open interval that only has to be true around 0, but let me just point out to you why this is true, or why we know this is true. this thing right here is always less than 1, right? So this value is always going to be a negative value, okay? So this, the most it can be is a negative value, but it's always going to be greater than that value, or the absolute value here will be greater. On the flip side, the exact same thing, except this value is always going to be positive. So since this is always less than 1, this value here is guaranteed to be sandwiched between these two things. It probably, if you want to confirm this, go ahead and give this a graph, okay? And I'm really only concerned around, so if you go -1 to 1, -1 to 1, you'll see that this is true. So this is your absolute value graph. This is your negative absolute value graph. And then what you see happens is the sin x graph, which is quite crazy here, sort of gets squeezed through this, which is exactly when we use squeeze terms. So I don't know exactly what it looks like, but it gets squeezed through here. Now, so since this is true, and since we know the limit as x approaches 0 of negative absolute value of x is equal to 0, which is also equal to the limit as x approaches 0 of the absolute value of x. So those are equal, okay? Then by squeeze theorem, we know the limit as x approaches 0 of x over sine 1 over x has got to be 0. So we have no way of doing this directly, at least not yet, but we are able to use squeeze theorem to squeeze it between these two values where we do know the limit. Okay, so that is section 1.3.